Welcome back to the AI Learning Series. You've made it to a truly pivotal moment. So far, we've explored the vast landscape of AI, peered into the learning mechanisms of machine learning and deep learning, and just last time, we mastered the art of preparing our data, the fuel for any AI engine. Today, we're taking all that foundational knowledge and finally doing something incredibly exciting. We're going to build our very first machine learning model. Learning objectives and what we'll do today. By the end of this session, you won't just understand how models are built, you'll feel confident in the core steps involved. Specifically, you'll be able to understand the workflow of building an ML model from prepared data to a working prediction. You'll learn how to select the right algorithm for your problem. Grasp the concept of model training and what actually happens. Discover how to evaluate your model's performance using key metrics. And finally, we'll walk through a simple, practical example of building a regression model. Get ready, because this is where the theory truly meets practice. Segment 1. The ML Model Building Workflow, a recap and overview. Remember our machine learning workflow pipeline? We've already covered problem definition, data collection, and extensively, data pre-processing and splitting. Today, we're focusing on the critical next stages: model selection, training, and evaluation. Building an ML model essentially involves choosing an algorithm, selecting the right learning algorithm for your specific task, training the model, feeding your prepared training data to that algorithm so it can learn patterns, evaluating the model, assessing how well your trained model performs on new unseen data, and refining, optional but common, adjusting the model or its parameters to improve performance. Let's dive into each of these. Segment 2. Choosing the right algorithm. The world of machine learning algorithms is vast, but choosing the right one often boils down to your problem type and the nature of your data. Recall our problem types from Session 2. If you're predicting a continuous numerical value, example house price, temperature, you're doing a regression task. Common algorithms: linear regression, decision trees, random forests, support vector regression, and neural networks. If you're predicting a category or class, spam, not spam, dog, cat, disease, no disease, you're doing a classification task. Common algorithms: linear regression, decision trees, support vector machines or SVMs, k-nearest neighbors, and neural networks. If you're finding groups or patterns in unlabeled data, example customer segments, you're doing a clustering task. Common algorithms: k-means, db-scan, and hierarchical clustering. For our first model, we'll keep it simple and intuitive. We're going to tackle a regression problem using one of the most fundamental algorithms, linear regression. Segment 3. The model training process. So you've chosen your algorithm. Now, how does it learn? This is where the training process comes in. Input data, features. You feed your pre-processed training data, the features, or X, to the chosen algorithm. Target data, labels. You also provide the corresponding correct answers, the labels, or Y, for supervised learning problems. Learning patterns. The algorithm then iteratively adjusts its internal parameters, like the slope and intercept in a linear regression line, to find the relationship between the input features and the target variable. It tries to minimize the difference between its predictions and the actual correct answers. Optimization. This adjustment process is often guided by an optimization algorithm that helps the model find the best possible set of parameters. Once this process is complete, you have a trained model. This model has learned from the data and is now ready to make predictions on new data it has never seen before. Segment 4. Evaluating your model's performance. Building a model is one thing. Knowing if it's good is another. This is where model evaluation comes in. Remember that test set we created in the last session? This is its moment to shine. We use the test set to get an unbiased estimate of how well our model will perform in the real world. The metrics we use depend on the problem type. For regression problems, or predicting a number, mean absolute error, MAE, the average absolute difference between the predicted and actual values. Easier to interpret as it's in the same units as your target variable. Mean squared error or root mean squared error. Mean squared error squares the errors, penalizing larger errors more heavily. RMSE is the square root of MSE, putting it back in the original units, making it more interpretable than MSE. R-squared, coefficient of determination, represents the proportion of variance in the dependent variable that is predictable from the independent variables. A value of 1 means perfect prediction. 0 means the model explains no variance. For classification problems, predicting a category. Accuracy, the proportion of correctly classified instances. Simple, but can be misleading with imbalanced datasets. Precision, out of all positive predictions, what proportion were actually correct? Important when false positives are costly. Example, spam detection. Recall, or sensitivity. Out of all actual positive instances, what proportion were correctly identified? Important when false negatives are costly. Example, disease detection. Confusion matrix, a table that visualizes the performance of a classification algorithm. It breaks down correct and incorrect predictions by class. Understanding these metrics is crucial for knowing if your model is truly performing well for your specific problem. Segment 5. Hands-on walkthrough of building a simple regression model conceptually. Let's walk through building a very simple linear regression model to predict, say, house prices based on their size in square feet. Here's what the conceptual steps would look like using a popular Python library called scikit-learn, which is often abbreviated as sklearn, which is a go-to for traditional ML algorithms. Import libraries. First, you'd import the necessary tools. Load and prepare data. You'd load your dataset, example from a CSV file, and perform the pre-processing steps we discussed in session 4. For simplicity, let's assume our data is already clean. Here, X would be our house sizes, and Y would be the corresponding prices. Split data. Divide your data into training and testing sets. We're typically using 80% for training and 20% for testing. Random state ensures our split is reproducible. Create and train the model. Instantiate your chosen algorithm and then fit it to your training data. This is the learning step. When model.fit runs, the linear regression algorithm is busy finding the optimal line or hyperplane in higher dimensions that best describes the relationship between house size and price in your training data. Make predictions. Use your trained model to predict on the unseen test data. Ypred now contains the model's predicted prices for the houses in your test set. Evaluate your model. Compare the model's predictions, or Ypred, to the actual prices, Ytest, from your test set. Based on these metrics, you determine if your model is performing well enough for your task. A lower MSE is better, and an R-squared closer to 1 is better for this problem. This entire process, from loading data to getting evaluation metrics, is the core loop of building an ML model. While this was a conceptual walkthrough, it represents the exact steps you'd take in a real project. Segment 6. Common pitfalls, overfitting and underfitting. As you build models, you'll encounter two common challenges. Underfitting. This happens when your model is too simple to capture the underlying patterns in the data. It performs poorly on both training and test data. It's like a student who hasn't studied enough and can't answer any questions. Overfitting. This occurs when your model learns the training data too well, essentially memorizing it, including the noise. It performs great on the training data, but poorly on new unseen test data.
It's like a student who memorizes answers to a specific test but doesn't understand the concepts, failing on different questions. A good model finds the right balance. It's complex enough to learn the patterns, but general enough to perform well on new data. We'll explore techniques to address these in future sessions. Wrap up and what's next? Wow! We just conceptually built our very first machine learning model. You've learned about algorithm selection, the training process, how to evaluate performance with key metrics, and even got a glimpse into the code. This session is a huge milestone. You've moved from understanding what AI and ML are to understanding how they actually learn and make predictions. In our next session, we'll move from building to deploying. We'll explore how to take these trained models and put them into action so they can start making real-world predictions.
What kind of model are you excited to build first? Let me know in the comments below. If you found this explanation helpful, please give this video a like and subscribe to the channel so you don't miss any future lessons in our AI learning journey. Here's a recap of what we learned today. ML workflow: select algo, train model, evaluate. Algorithm choice depends on problem, regression, or classification. Training: model learns from data, adjusts parameters. Evaluation: use metrics like MSE, R2 for regression, ANL or accuracy, precision, recall, and F1 for classification. Beware: underfitting, too simple, and overfitting, too complex. Thank you so much for joining me today. I can't wait to see you in the next session as we bring our models to life.